So let's finish off looking at the fast inverse square root algorithm. Now, we know the algorithm is of this form here. And we know in terms of a 32-bit number, the value for our L is going to be 2 to the 23. So 23 is just the number of mantissa bits. And the value for our B, which is the bias, is a value of 127. So this number here, which is our magic number, is the number 1598029824 in decimal. Now the actual magic number that tends to be quoted for a 32-bit floating point number is slightly different from this. And we'll talk about that in the next slide. But first of all, let's just stick with the number that we have generated and see whether it actually works. So the algorithm is really simple. We work out the value of our floating point number, and then we work out the integer equivalent of it just using normal binary. We divide it by 2 and we subtract it from this magic number. So let's say we're looking at the number 4. So this is the number 4 here in 32-bit floating point. So we can say here that y is equal to 1 upon root x, x is 4, y is 1 upon root 4, which is 1 upon 2, which is 0.5. So when we run through this little algorithm, we should get the number 0.5. So we take this here, which is our ix, we take this here, which is our floating point number, and then we generate ix. So we just change this into the actual integer representation. So the integer representation is this number here, which we've seen in a previous video. So the value for our iy is going to equal the magic number minus this number here divided by 2. So this will give us this number here. Now whenever we take this number here and we represent it in binary format, so this is just a simple binary format for this number, and then we convert this binary format back into the number y. So we take this here and we convert it back into the number y. We're actually going to get y is equal to 0.5. So in this instance, with this particular value for our magic number, and whenever we look at working out the inverse square root of 4, it turns out that this is a bit of a fluke. We actually get an exact result. So I happen to have picked a value here that gives an exact result. Now that wouldn't normally happen, and in fact if I was to choose most other values, we wouldn't get exact results. So it's a bit of a fluke, this, and it's a bit strange, and it's a nice one to actually to find. Now if we were going to use the actual magic number, we would get a different value from this 0.5. So let's go ahead in the next slide and we will look at the actual magic number, and we'll put that value in, and we'll have a little bit of a talk about where the actual number came from. So the actual recognized magic number in hex is this one here, and this is the one that you'll tend to find if you go looking for it online. Now the actual integer equivalent of this is this number here. So we've got our actual computed magic number from here. So if we were to look at a percentage difference, we could put the actual number divided by our number times 100, and you can see we're accurate to within 99.96% of the actual value. Now the magic number that we actually see here was generated empirically. So really by observation and experimentation. Also, you can generate particular magic numbers in order to optimize certain performance criteria. Now, I'm not going to get into any detail here. You can always have a hunt online and you can look under magic number. So it means that the standard magic number is this number here. And the primary goal of using this particular number and the fast inverse square root algorithm is to achieve an efficient and sufficiently accurate approximation for use in real-time applications such as 3D graphics rendering, where the performance is critical. So this has given us a good introduction to the fast inverse square root algorithm. I will produce one more video where we will code it in Python, and we can also run through some analysis just to see how accurate this form of division and square root is going to be for us. If it's accurate enough for us to get, say, 3 decimal places of accuracy over a wide range of values, then we can use this method in order to generate a division and square root function for our 16-bit floating point unit. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.